Just gonna give it a few seconds for attendees to join. Okay. Hello everyone. Welcome to today's webinar on manure management and greenhouse gas emissions in sub-Saharan Africa. Today we have, my name is Lungi. I'm the GRA Secretariat for today's webinar. Today's webinar is being recorded and will be available for future viewings in the GRA website. Today we will have 3 presentations with brief clarifying Q&A sessions following each presentation by a panel of Q&A answers session. We have a Q&A chat section, so you can post your questions there and they will be answered by the presenters and panelists. If you see a question that you like or agree with, please upvote and use the upvote button so that we know that the question is the popular one. And if your question is not answered or you see it's being dismissed, this doesn't mean that the question won't be answered later. Questions will be summarized and the additional answers will be made available on our website at a later date. So first we have, I'd like to welcome our presenters, David Pelser, Sonia Leitner, and Martin Ngwabi. Our first presenter is Dr. Pelser, who is a soil scientist at Agriculture and Agri-Food Canada, specializing on nitrogen cycling in agricultural systems with a focus on measuring and mitigating ammonia and greenhouse gas, specifically methane and nitrous oxide emissions related to agriculture. Dr. Pelser also worked as a scientist with the International Livestock Research Institute in Nairobi, Kenya, measuring and investigating practices to help mitigate greenhouse gas emissions from manure and soil management in smallholder agricultural systems. Over to you, Dr. Pelser.
All right, thank you. Just work on sharing my screen here. So let me know if you can see my screen and if you hopefully see it in presenter mode. Is that in presenter mode for everyone? It's good?
Yep.
Okay. All right. So yeah, my name's David Pelster. I'm a scientist with Agriculture and Agri-Food Canada. I'm based in Ottawa. But I'm not going to be talking about the work I do here. I'll be talking more about the work I was doing when I was still in Nairobi. Yeah, I'll be talking a little bit about manure management practices. The title is Knowns, Unknowns, and Policy Implications for Sub-Saharan Africa. So first thing, I'll talk a little bit about some of the farms. I think Sonia will talk a little bit about this as well. There's a paper a few years back by Ken Giller's group, sort of characterizing farms a little bit, typical farm size across much of sub-Saharan Africa. They're very small. They're often mixed between crops and livestock. There's dryland systems as well, which tend to be more pastoral. I didn't really work much in that, so I won't be talking so much about the pastoral systems. A lot of the farms, they're not food self-sufficient. Part of that's due to the yield gap, which is related to, generally related to insufficient inputs, but the lack of self-sufficiency is also due to limitations associated with farm size. But because you do have that yield gap there, improved manure management should be able to help a little bit. So very quickly, some of the existing practices, dryland grazing, it's usually beef cattle, and the manure management is either, it's not really managed because it's deposited in pastures, but then overnight, the animals tend to be put in what are called bomas or kraals. And then you have a lot of manure kind of being stockpiled in these. So about 80% of the livestock housing in sub-Saharan Africa tends to be in these sorts of systems, and the manure management quite often is deep bedding or collected in heaps, but it's not covered. And then, like I said, the manure is also deposited directly onto the pasture with no real manure management. So a couple photos that I took still from when I was working there. On the left, you see the inside of a kraal. You can see the manure has been kind of piled up. It's not covered. It's exposed to the sun, and it's drying out. So that means you're losing a lot of nutrients. The farmer on the right, he is mixing in a lot of crop residues and stuff. So trying to form a little bit of a compost heap, but again, it's uncovered. So there's also, especially in certain regions within sub-Saharan Africa, the highlands in Kenya, Tanzania, Uganda, and in other Ethiopia as well, and other regions, there's still a little bit of grazing that happens, and you can see that in the photo on the left. So it's not your typical dryland areas. They are getting, it's a bit greener, but they still do some grazing up there. But they do a lot of what's called cut and carry. So you can see in the middle photo, the one farmer, he had been, went into the forest, cut a bunch of grasses, and now he's taking it back to his cattle. And the housing looks a little bit like you see on the right there. It's quite often the housing is covered. Some of them would have sort of concrete floors. And then you can see just outside in front of the, let me just grab laser pointer here. So you can see right here, hopefully you can see my laser pointer, that's the manure heap there. So again, the manure is uncovered and just sort of left exposed to the rain and the sun, which is probably not the best system for it. You tend to lose a lot of your nutrients that way. Either ammonia volatilization can happen. You could have nitrate leaching if it rains. So not quite the best management practice, but yeah, that's sort of the way it's done for now in many of these places. So there is in these sorts of systems, with these sort of mixed crop livestock systems, there's a bit more variability in terms of the manure management. But even still, according to a lot of the studies, about 70% of the manure is going to be heaped, and more than half of that is just left uncovered. So I won't be talking about any of the mitigation options. I think some of the following speakers will talk about that. So if you look, this is from a paper that was published, actually it's quite a while ago now. I think it was 2016 or 2017, but we looked at all the different manure management practices and across a number of countries in sub-Saharan Africa. And you could see in Central and Western Africa, a lot of pasture, some dry lots, solid manure, and then fuel. And then in Eastern Africa, you could see, again, quite a lot of pasture. So just manure being deposited in the pasture, a fair bit of dry lots. And then some solid manure storage, and that'll be your heaping. And then fuel, so drying and then burning of the manure for fuel. That was beef beef manure. If you look at other types of manure, so backyard chickens tends to be just free range chickens. The broilers, they would be inside, but a little bit of, or a lot of litter for the broilers, pretty much 100% actually. And then the laying hens, again, some of the manure would be stored in pits. Pigs, very quite variable. There's, these sort of backyard pig operations, and there the manure can be anything from solid to pit to anaerobic digestion. But there's a lot of variability out there. If you do have pits, or in this case on the left you see an anaerobic digester sort of in the background, and then the manure is stored in the pit. On the right side, that's a compost pit. So there's quite a bit of variability out there. This is this farmer, he has a biodigester, and then the overflow or the outflow from the biodigester goes straight onto the field. So it looks a bit messy, but you can see there's the manure going onto the field as a way of managing the manure, I guess. But liquid manure is still quite uncommon. It was done here and in the previous slide, but it's only about 9% of the farms. And with these liquid manures, about 55% of the slurry, 55% of the farms, they'll store the slurry in the pits, and then the other 45%, it'll be applied directly to the field. And that's sort of what we're looking at here. Some of the farmers that do manage with liquid manure, they do separate the manure and the urine, or the dung and the urine, which is interesting. And then, like I said, the dried manure, and that's a little bit more common in places like Ethiopia, where they dry the manure and then use it for cooking. Apparently, they like the quality of the flame for making injera, the local bread. And that tends to be the farmers closer to the city tend to use the manure a little bit more, and that's because they can't access wood as well as the ones that are a bit farther away from the cities. So it is a bit, there is a little bit of regional variability in that. So there's a lot that we don't know about manure management still. In East Africa, and that's sort of where I worked mostly, there's not that much literature on it. A lot of it is gray literature, so not peer reviewed. I looked through a few reports, and the estimates they had were often based on expert opinion. So, some actual survey data would be quite useful in a lot of this. There was 15 studies that I found. 80% of these were from East Africa and 20% were from Southern Africa. Martin, one of the later speakers, he'll talk a little bit about what he's found in West Africa. So I guess I just wasn't looking hard enough, because it seems like there is some information on Western Africa, which is good. The other thing is that 75% of the studies I found were on small mixed farms, and we know that pastoral systems can still be quite large production systems, and that's an important one that we've kind of missed. And then Central Africa, I'm not sure if there's much study going on in there. We also did a report a few years back, sort of a global assessment of manure management policies and practices. And I'll talk a little bit about what we found for sub-Saharan Africa. We surveyed the policies in 12 sub-Saharan countries. All 12 of them had national policies. The Minister of Agriculture had national policies in all these. And then a lot of them also had policies related to livestock manure from other ministries, so Ministry of Environment, Energy, and Public Health. And there tended to be a lack of coherence between the different policies. And all of the countries that we found, they had poor enforcement. And these were based on surveys we did of people within those ministries. They all agreed that enforcement was not great. So some policy implications. The legislation we know is often developed by policymakers with not a lot of knowledge of existing farm practices, tend to be driven by broader national goals. seldom enforced due to weak coordination, and then there's quite often unclear rules and penalties for non-compliance. So I'll finish off with this slide. Basically, from what I've seen, need better alignment between the policies across ministries. Sometimes they're not even, they're almost contradictory in some cases. Clear rules, penalties, and enforcement is very important as well. And then I think better incentives for improved practices would be helpful as well. And that's it for me. So thanks, and I think it is, I could stop sharing my slideshow then, and I think it's time for questions. Is that right?
David, this is Sven Sommer. I'm so sorry that I didn't come at your time. I thought it was 3 o'clock Kenyan time. I should be contributing. So it's really, I apologize everybody listening that I have not been here. So, but I'm Sven Sommer. I'm the co-chair of the Manure Management. And so once more, sorry.
No, that's okay. I think I went a little bit long because I didn't have someone like cutting me off. So
yeah, thank you. Well, I hope everybody will still have enjoyed to be there, because I think it's such an important meeting. So I cannot introduce you. So I would just like to ask you a question, maybe to start a question. It's you have this talk about learning and competences and alignment between policies and enforcement bodies. So that was one of the questions I would like to ask you is how can, if we would like to make a relatively nice large project where we had a focus on how to manage manure to reduce greenhouse gases and to make the manure of use more efficient, how do you think it can be done? How much can be actually in Africa? There are skilled scientists and competent scientists, but maybe not in this area. Manure may not be in focus. So how should we proceed after this marvelous meeting?
Wow.
Sorry.
That's a loaded question. Thank you, Sven. I mean, I think, you know, there's still a lot to be known. I mean, we know, and I think Sonia will be talking a bit about some potential mitigation strategies. I mean, but when it comes to policies, like I think the weak compliance, and then so like some of the other stuff that we saw, for example, in certain countries, like a lot of the information on management practices is passed on to the farmers through extension services. And there was at least a couple countries where the extension workers would receive bonuses based on the amount of fertilizer they sold, or that was sold within the area, which almost, you know, if like I can understand, given the yield gap, they want to increase yields, and you know, synthetic fertilizers is one way of doing things, but you know, it almost creates a disincentive for proper manure management, because the extension workers can get more of a bonus if people use manure less and synthetic fertilizers use that a little bit more. So, you know, we'd need to look at things, you know, sort of policy or incentives that almost disincentivize good use of manure. I think, you know, a lot of it, you know, from the management perspective, I think a lot of the farmers, they see the manure and they realize that it is, you know, a source of nutrients, but the level of education isn't that high in a lot of these areas. So providing good educational information, like either through the extension services or, you know, like just sort of handouts, like one pager or like brochures type things that could be passed on to the farmers. explaining, how and why. But, some of it, a lot of these smallholder farmers, they try to, manage a whole lot of things. And, sometimes, I didn't even mention the application timing. A lot of times the manure will sit in a heap for, a year and a half before it's actually applied. And sitting out in the open, it's not really that useful. It loses a lot of at least nitrogen between, when it first is heaped up and when it is actually applied. But if you try to get the farmers to apply it more frequently, sometimes there's labor constraints coming in. If it's just a single farmer, he's got animals to look after, he's got his fields to go out and seed and weed and everything else. There are labor constraints, and I mean, I'm not sure how to fix that, but I think probably working with the extension services and improving the incentives might be one way of doing things. That would help improve. What the scientists can do, I think we already we have some ideas on improved management, and I think it's just a matter of getting the information out there. And
Other questions, or is
there's a question in the Q&A from Titus Septini. I hope I said that name. And it says, to collect manure management data, how do we define practices that are not well described in the IPCC guidelines? And that's a good question. I mean, yeah, like maybe we need to expand a little bit on the IPCC guidelines, or can we find ways to do, a lot of the manure management practices that I saw, and granted, I was there for 5 years, so there's probably there's a lot of things I didn't see when in my time there. But a lot of it, might not be a perfect fit in some of the IPCC categories, but you can make a strong case to group it in one or the other. I mean, there's lots of different ways people do things, but at some point you just have to, classify it somewhere. And if it's not a perfect fit, that may not be the worst thing ever, I guess.
I could ask one more question. It's about when we look at agriculture, it is also about economy. So how can we tell people about the economically benefits of using manure efficiently? Is that the way to go, or maybe we should ask our colleague from Africa about this?
I don't know. Maybe we'd talk about this in some of the later talks, but I mean, like the economic benefits of it, like, I mean, I worked a little bit in Malawi with some of the extension workers there, talked with the extension workers, like mainly Eastern Africa is where I worked, and a lot of that, it's the extension workers who talk to the farmers. I mean, as scientists, there's, so many, we can't access the farmers directly, I don't think. I think we have to use government extension services and try to educate the extension service workers, and give them the materials that they can use to actually then go and talk to the farmers. I think that's probably, I mean, I don't know how many millions of farmers there are across sub-Saharan Africa, but there's not enough scientists to do that. So I think we can produce sort of material that we can then share with the government extension workers, and then they can go out and talk about these things.
So maybe I should go to be the leader of the chair. And if there is one more question and a short answer, then we'll go to the next presenter.
Okay.
So according to mine, then it's next is Sonia. Is that correct? So yeah, Sonia, my good colleague, or from ILRI, who has been working with manure and composting and also recycling somewhat. You will now give a presentation about manure management in East Africa. I'll just take the short cut of your title. So the word is yours, Sonia.
Thank you very much, Sven. Can you confirm that you can see my screen and that you can actually see it in presenter mode?
Yes, I can see it.
All right. Thanks for the introduction. It's my pleasure to be here. My name is Sonja Leitner. I work at the International Livestock Research Institute here in Nairobi, Kenya, where I've been based for the past 7 years doing research on manure management and nutrient cycling. And I work both in smallholder mixed systems as well as pastoral systems. And I will give you some examples of what the situation looks like and some of the interventions that we're looking at to reduce greenhouse gas emissions and also to better balance health risks. So, okay. So broadly speaking, we can, yes, everything okay? All right. So broadly speaking, we can categorize agricultural systems into mixed crop livestock systems and pastoral systems. I will be talking a lot about cattle, but some of these findings are also relevant for other livestock systems. So let's start with the mixed crop livestock systems. You just heard from David that manure management basically starts with animal housing, and we have a bit of a gradient of time that the animals spend inside the housing. So we have these semi-intensive, or sometimes also called semi-grazing systems, where the animals spend roughly a third of their time grazing. And then on the other side of the spectrum, we have cut and carry systems or zero grazing, where animals are confined most or all of the time. And the system determines the housing structure because building animal housing costs money. And I'm showing you these two examples of what I've seen in the field. So on the left side, you see an example where the animal is standing on an earthen floor. There is no roof. The housing is basically built directly under a tree. And you can see that the animal is quite dirty and there's a lot of manure. So you can already tell that this animal housing is not cleaned out very frequently. And this brings not only problems with nutrient losses, but also with health risks. You can see the animal has some manure on the legs. And this here in the back is actually the watering trough, which is contaminated by manure. So disease transmission through manure is a big problem. And on the right side, you see a more positive example from a manure management perspective. So you can see there's a concrete floor, there's also a roof, and the housing is cleaned twice a day in the morning and evening. And in this case, of course, frequent manure collection helps to preserve nutrients and to reduce disease transmission. So if we talk about manure management interventions, we have to start at the animal housing. And this is something that's very often overlooked in my view. Then here you can see some examples of what manure management looks like in East Africa. So these are examples that I've collected from Kenya, Tanzania, Uganda, and Ethiopia. And you can see that the majority of manure is managed as solid in heaps, very often with bedding, sometimes also mixed with feed refusals or kitchen waste. Most of the time uncovered and on an earthen floor, so exposed to sun, exposed to rainfall, and this reduces the nutrient concentrations of the manure. And the problem is that the feeding conditions on many of these smallholder farms is also suboptimal. So many of the animals don't receive enough feed throughout the entire year. There are times of feed scarcity during the dry season, and also feed quality is often not very rich in protein. And then the manure that the animals are producing has low nutrient contents. And if you then store it like this, you lose even more nutrients. So you can imagine that what is brought to the crop field is not a very high quality fertilizer. So this is basically one of the points where we need to also think about with interventions. I've also mentioned health considerations. We're not only facing disease transmissions through animal manure, but there's an increasing problem with antibiotics and antimicrobial resistance. So 90% of the dairy farmers in Kenya use antibiotics, very often preventatively. And depending on the drug, between 40 and 90% of administered antibiotics are excreted into animal manure. So we wanted to know what that means for greenhouse gas emissions. So we did a manure incubation experiment. Here at ILRI, we collected antibiotic-free manure from the barn. So we only used animals that had not received any antibiotics for the past 6 months. We mixed the manure from the herd and then split it into open buckets. You can see them here on the bottom left. And then we spiked them with the 3 most commonly used antibiotics for Kenya, which are tylosin, enrofloxacin, and oxytetracycline. And all antibiotics were used in high and low levels to represent common dosage situations. And then we measured greenhouse gas emissions with a Picaro laser, as you can see here. And in summary, this is what we found. Here you have the methane emissions, nitrous oxide, and the global warming potential. And those are the different treatments. So the blue one is the control, and the others are the antibiotic treatments. And what we found was that all antibiotics increased manure methane emissions, and 3 of 6 antibiotics treatments also increased manure N2O emissions, which wasn't quite what we had expected. We thought antibiotics would actually reduce microbial activity and with that reduce emissions, but we found the opposite. And in fact, the manure with antibiotics had 3 to 4 times higher global warming potential than without. And this has implications because apparently something really happens to the nutrient cycling processes. And also this basically means that manure emission factors might underestimate emissions because antibiotic use is usually not considered. And going further, we also looked at the decomposition of antibiotics over time. So here you have the 3 antibiotics, tylosin, oxytetracycline, and enrofloxacin. And this is on the y-axis, the concentration, and here over time of the incubation experiment. And note that there is a y-axis break here, that's the dashed line. And basically the concentration of antibiotics went down over our 4 months incubation experiment, but antibiotic residues were still detectable after 4 months. So what does it mean? This means that if this manure is applied on crop fields, it can affect soil nutrient cycling. It could potentially also affect soil greenhouse gas emissions. And it can lead to accelerate the spread of AMR, of antimicrobial resistance into the environment. And there currently are no guidelines for acceptable or safe antibiotic levels in livestock manure, because even small traces can lead to development of resistant microorganisms. Okay, that was the situation. Now let's talk a little bit about interventions. So we started recently to test some interventions to reduce emissions and reduce nitrogen losses from storage. And the first one, or one of the first ones that we did, was on biochar or charcoal addition. So biochar has received quite a bit of attention in crop trials in Kenya and Uganda. Sorry, because it works quite well in these highly weathered tropical soils that have low carbon contents. And you can see positive effects on the yield. So we thought, okay, why not start earlier? Why not add the biochar or the charcoal during manure storage? And because not every farmer has access to biochar, we also compared it with regular charcoal, which is very commonly available. So we used cattle manure. We used the same buckets as we did in the antibiotics trial. And then we added biochar or charcoal in 2 different levels at 10% and 30%. And for biochar, we also tested the effect of steam activation. So sometimes to make it more, to make the surface area bigger, biochar is sort of cleaned with steam before applying it to the field. So we tested if that also has an effect. And we measured greenhouse gas emissions and ammonium volatilization with the Picaro. And here are our findings. We found that 30% biochar addition reduced nitrous oxide emissions, and all biochar treatments and the 30% charcoal treatment reduced ammonia volatilization. And we suspect that the reason for that is that the big surface area of biochar and charcoal can bind nitrogen, and with that reduce the volatilization of ammonia and reduce the transformation into nitrous oxide. So this might be an option to reduce nitrogen losses from manure storage. And we saw that biochar was a bit superior compared to regular charcoal, most likely because it has a larger surface area. We also looked, or we are currently looking at the potential of composting to reduce health risks and make a good fertilizer out of the manure. So we have an ongoing composting experiment, which we just started a month ago. So the buckets are standing behind my office in front of my window. Basically, we're doing this time a larger scale experiment. So we have these big containers. Each of them is filled with 200 kilos of cattle manure mixed with straw. And we use the ratio that is comparable to what you would find in smallholder systems. And the treatments we're looking at, so we have the control, which is unturned to simulate a normal compost or a normal manure heap. Then we have a composting treatment that is turned 3 times within 2 weeks. Then we have composting plus covering. We added a straw layer to basically see if it can help to increase the heating of the manure even more. Composting and biochar addition as a way to mitigate some of the nitrogen losses, and a combination of all of those. An experiment is ongoing, so I cannot show you much, but this is basically the temperature of during the first 2 weeks. And the dashed line here, this is the 50-degree threshold. And temperatures above 50 degrees can help to sanitize the manure. So basically, they help you to kill off pathogens in the manure or even weeds. And we were quite happy to see that for a full week, all our treatments reached temperatures far above 50 degrees. And this blue and purple line here are the 2 treatments with biochar. And you can see that biochar addition basically prolonged this this thermophilic period for half a week more. And those arrows are the time when we turned the compost. That's why you see these dips in temperature after the turning, and then it shoots up again. We also looked at, well, not at pathogens directly, because our cattle here were healthy, so we didn't find substantial amounts of pathogens in the manure, but we used indicator species, E. coli and coliforms. And those are basically commonly used in composting experiments as indicators for pathogens. So if you reduce them, most likely you will also reduce pathogens. And in all the treatments, these microbial indicators went down within the first 2 weeks of the experiment. So it seems that composting is indeed effective to sanitize manure. And the thing that made us very happy is that it was just a simple manure heap with a bit of straw. So previous composting manuals often speak about using woody or carbon-rich materials and manure and nitrogen-rich leafy materials and ash and soil. So it's a bit complicated to collect all these materials and build a compost heap. And here we basically just used what a farmer might also collect from the barn, and it started to heat up. So I think this is a very positive finding. And now we're evaluating also the effects of biochar to mitigate some of the nitrogen losses that you can have when you do composting. Okay, so enough about the mixed crop livestock systems. Let's talk about the pastoral systems, because as David said, they are usually overlooked when it comes to manure management. Something that you will very likely come across or have come across if you've ever been in pastoral regions of East Africa are these traditional overnight enclosures, also called bomas in Kiswahili. You can see an example here using metal fencing. This is at our Kapiti research station here in Kenya. And here on the bottom right, you can see an example of a boma in Tanzania that uses wooden fencing. And basically these bomas are built to protect animals from theft and from predators overnight. So the animals are confined overnight, and then they spend the day out grazing in the savannah. And because they spend half of their time in bomas, also half of the manure is deposited into bomas. And the important thing to note is that these bomas are usually not cleaned. So manure is left to accumulate, and we've measured quite high nitrogen loads, 7,000 kilos of nitrogen per hectare and more, because these bomas can be in use for months to years at a time. So we thought, okay, these bomas are most likely greenhouse gas emission hotspots. So we measured emissions from bomas, and we calculated the farm gates greenhouse gas balance for our Kapiti research station. So here you have the methane emissions and nitrous oxide emissions expressed as ton CO2 equivalents per year. And these are the different sources that we measured. So we measured grassland, but basically the background emissions, the enteric methane from the cattle, manure deposited on pasture, and manure in cattle bomas. And what we found was that over 30% of the nitrous oxide originated from cattle bomas. And why is this relevant? Because cattle bomas or any type of bomas are usually not included in greenhouse gas inventories because there's no category for it. So we just had this question in the Q&A, what to do if you work with manure systems that are not following IPCC inventory. So basically, one might think they somehow represent dry lots, but national governments don't collect this information because a dry lot is a bit different from a boma. In a dry lot, you would feed the animals with grain and energy-rich food. And here it's just a way to confine your grazing animals overnight. So this is something that we need to work on to raise more awareness here. But they're not just nitrous oxide emission hotspots. There are also nutrient reservoirs that are not being used because in a way, the nutrients are collected in the grassland during grazing and then transferred to the bomas. So we thought, okay, what can we do to move these nutrients back to the grassland? We didn't use, or we didn't think it would be make a lot of sense to spread the manure from the bomas because in pastoral systems, you won't find heavy machinery that's needed for that. So instead we thought, okay, let's move the bomas. So we started using short rotation bomas on the Kapiti ranch. And the bomas are being relocated every 2 to 10 days. Before it used to be every 1 to 4 months. And you can see what this looks like here quite impressively on these pictures. So this is the start of the experiment. We have 3 bomas. Each boma holds between 100 and 140 cattle. This is what it looks like after 4 months. So you can see how the bomas move across the landscape. And this is the same site after 2 years. You can see the vegetation is already coming back. And the nice thing is if you move the boma more frequently, you have lower local nitrogen concentrations, you have less trampling from the animals, so you have lower greenhouse gas emissions and also less soil disturbance. So the vegetation recovers faster in these short rotation bomas. And as soon as the vegetation is back, the plants take up nitrogen and this reduces N2O emissions. Plus, we also see that pasture in abandoned bomas contains more protein, which helps to increase livestock productivity. Of course, we can later on discuss how feasible this really is for pastoral communities. Anyone who has ever been in any kind of pastoral system might have seen that traditional bomas are often constructed from wood or even thorny acacia shrubs. You certainly don't want to move that every two days. So we need other solutions for this as well. But basically what it shows is that we're sitting on a nutrient reservoir here that we could think about how to use for the grassland. And with this, I'm coming to the end of my talk. And yeah, because with Sven, we discussed, okay, we use this webinar not just as a way to give information to an audience, but to hopefully also attract some ideas for future research. And I thought about some pressing research needs that I think should be addressed. And the first one for me is really to develop manure management options that are feasible for smallholder farmers and that can work for different livestock species. And we really need low-tech options for the poorest and most nutrient-constrained farmers. So currently, there's a bit of a trend that investors or donors like to promote, how can I say it, very technical, shiny solutions. And I'm from Austria, and in German, we have the saying, to shoot birds with a cannon. It seems sometimes a bit like that. So you come with very technical solutions that are very top down, and then the uptake is quite poor. We should not make this mistake and instead look for simple interventions that are co-developed with the farmers to make sure they're also feasible. And of course, we need manure management options for pastoral systems, not just to reduce emissions, but to return nutrients back to the grassland and to help combat land degradation. And in all of this, we should, of course, quantify and reduce nutrient losses. We've done a bit of work on greenhouse gas emissions, but we need to also look at the big nitrogen loss pathways, which are ammonia and denitrification and leaching. And in all of this, consider the health aspects of manure management, pathogen and AMR reduction, and balancing it with trade-offs. Thank you very much.
Thank you very much, Sonja, for a very nice and interesting presentation. I heard a lot of new things in addition to what I learned for 2 months in Nairobi. So I could see there was one question. So I would like to start with that one. Wasn't it written for?
There are a few questions in the Q&A section.
Yes. Can you see them, or shall I?
Yes. So one question is from Francisco Salazar, who is asking, in composting and biochar use, will you expect an effect also on antibiotics? Yeah, we have thought about this. In fact, that's the plan basically for the next incubation. You can see I really like doing these incubation experiments. And we thought it might really make sense to do a combined experiment where we do aerobic composting to see if that can decrease the antibiotics levels faster, and also to see how that affects the microbial community composition. And we're currently doing a more in-depth analysis of the community composition using metagenomics, because we really want to know what is leading to these shifts and why are emissions so much higher in the antibiotics treatments.
And there's also a question, if I'm jumping maybe, but about if will this heating affect the nutrient content of the compost and also the quality as a fertilizer?
Yeah, so the problem, let's say like that, with composting is that you basically really promote decomposition, which means you're also promoting the nitrogen cycling, and with that also the nitrogen losses. So composting can increase ammonia volatilization and N2O emissions. And the idea is that the biochar can hopefully absorb some of that nitrogen to prevent these losses. Regarding the fertilizer quality, there are like 2 ways to look at it. The one way is to look at basically the absolute nitrogen content. And basically, if you would like to maximize that, then the best way to do it would be to really collect all your manure and really store it airtight, compacted to really slow down decomposition. The problem is if you do that, whatever helps you to preserve nitrogen will also help you to preserve pathogens. So you might have a health problem. Plus, manure is more than just nitrogen addition. So through decomposing or composting, through decomposition, you're kind of creating a soil amendment that doesn't just act on the plants, on the crops immediately after crop application, but that has long-term effects. So it's not so easy to answer this question. And we were really discussing what should we prioritize. And we then said, okay, the health and safety must come first. So our aim is to first really make sure we reduce pathogen loads and increase, like make the manure safer. And yeah, if we then lose a bit more nutrients in the way, that's kind of the trade-off that we're willing to take.
And then there are questions that can be, that may give a long answer, but it's about the system you have analyzed and how is this, will this affect the IPCC calculations, you could say, now if you're using this standard manure management approach, or if you use the approach that you are hinting on that could be for the future. I don't know if you can do it short because we don't have much time, I'm sorry. But I'll tell everybody there is this meeting global in October where you are on the greenhouse gas emissions conference where they can talk with you.
So we looked at greenhouse gas emissions. We looked at emission factors, and some of the emission factors that we found were higher than the IPCC reports and some were lower. So I think just using a standard default factor will not give you the most accurate results. But what I think is an even bigger problem is that we're not considering some of these sources, such as the biomass. And I had a little bit of engagement with policymakers here in Kenya. And of course, they're not very happy when you tell them, hey, you're missing a big greenhouse gas emission source in your budget because everyone is trying to reduce emissions. So if I tell them, okay, you now have to add biomass, it will increase the emissions from the livestock sector, which people don't want to hear. So there's a little bit of a barrier against that. And I generally think these IPCC guidelines, I mean, they're absolutely great. And I really admire the tremendous amount that went into it, but they're also slow to change, obviously, because people are trying to harmonize across systems. But countries can also use their own methodologies. So I know that my home country, Austria, is not following IPCC to the dot, but for certain areas, we have our own different types of calculating emissions, which are also accepted. And I think for African countries, this is also possible. Of course, the question is if the willingness to do so is there.
Yes, I'm so sorry. There are many very good questions, but maybe we can ask the Secretariat to write it down and we can then put it on the homepage because I think it's time for the next presenter. So I'm so sorry about that, but it's great that there's such an interest. So I think we will say thank you to you, Sonia, for a very nice presentation. So and then I'm sorry with my pronunciation of your name, Inka Martin Navabi. So you may help me saying that correctly. You are the next presenter. You'll present us, give us a presentation, methane emissions from manure management in West Africa. So thank you once more, and I'm sorry we didn't have more time for this good discussion. So we go to a new.
I think we might have more time for the discussion because it looks like Martin's been having trouble with his connection. So
okay,
might have time for another question for Sonia.
Yeah, there are several, but maybe we can combine one that it's that composting is requires capacity and some infrastructure to carry that out, and the next one is also if smallholder farmers can actually get the bioreturn that you propose they're using. So maybe you can combine these two in your response.
Yeah, absolutely. So of course, composting requires some training and awareness. I know that other people already started doing a bit of composting training. The uptake has been mixed because people see it as a lot of work, and labor is always a cost factor. So that's why we try to make it as simple as possible by just using a mix of manure and straw. And basically the recommendation would be to make a manure heap, and once it starts heating up, you turn it 4 or 5 times in the first 2 weeks or so. So it's a relatively short period of time, and then you just let it sit. So I think it's realistic to do if we can really demonstrate the benefit for health. So I think that is an argument that people might be susceptible to show that it makes it safer. And yeah, I have some anecdotal evidence from one of my students who is also an extension worker, and he has done some work with smallholders on different types of composting. And after some time, they were convinced because they saw, okay, there's really a benefit also regarding the yields. So I think, yeah, I'm optimistic that it can be done. And in terms of the biochar, yeah, the big point is, of course, to use waste materials to produce biochar. We don't want to cut down forests to convert them into biochar. That would be beyond the point. But there are some systems ranging from very small, basically cooking stoves, where you can also where you have basically a little chamber where you can use waste materials to make biochar in small portions every time you cook. And then there are some medium-sized traditional kilns, and then there are also larger scale biochar systems here in Kenya. For example, some of the tea producers use it because they produce biochar that they apply on the tea farms, and they also the combustion process produces a gas, the syngas, which can also be used as a fuel. And they use that to dry the tea leaves. So basically, it really helps them to reduce their wood demand. So there are some examples of systems that can work and that are accepted at different scales. And that's basically one of the avenues we're trying to go.
Thank you very much. I think, sorry, I cannot pronounce your name, Martin. But I think the time has come for you to give your presentation about methane emissions from manure management. So, is it gone again? Yeah, there you are. So, the teams are yours.
Yes, can you get me now?
Yes,
Yeah, please, I would like that my presentation should be shared. I have issues with bandwidth here, so I can't really link up with my computer.
Okay, let me share my screen and share your presentation.
So while that goes on, I'm Martin Gwabi. I'm a researcher working on greenhouse gases and climate change. And I've been working in this area for about 10, 20 years now. And for the past 10 years, I've been working in this domain in Africa and particularly in Cameroon. Presently, I work as the head of department for agriculture and environmental engineering in the College of Technology, the University of Bamenda. And I've tried to build a small research network in this area in Cameroon and in Africa. So I have some collaborators in the University of Buea, and in the University of Bamenda, I have a host of postgraduate students that I'm working with. Thank you for the slides. Yes, as I said, I have a host of postgraduate students in the University of Bamenda that I'm working with, and in particular, I would like to appreciate the contribution of Andy Vadazak of AFC Canada, with whom I've worked also for quite a while. So next slide. Next slide. Yes, please. We're talking of West Africa here, and I put this picture just to southwest of Africa. That's West Africa, and it is characterized by heavy rains and dry weather, and it has a long rainy season and a short dry season, with a large temperature fluctuation. And it's important to note this aspect because they have a huge impact on greenhouse gas emissions, especially from manure management. Next slide. Yeah, so as a background, in West Africa and sub-Saharan Africa as a whole, the consumption of meat, that's poultry and pig, pork and egg, has increased drastically. And it's expected to increase about 6-fold by 2050. So this shows that the production is also increasing to catch up with this consumption rate. And for production, again, as has been presented, cattle are predominantly kept outdoors in the rough terrain of sub-Saharan Africa, and they do thrive there very well. Of course, here in West Africa, it's mostly on beef cattle production. So the highlight is that the dairy cattle market is not really as on the same level as beef cattle. Again, for production, we have sheep and goat, which are predominantly kept outdoors. It implies that there's huge quantities of manure, which is kept in those enclosures and also in outdoor fields. So when the enclosures, we expect to have hotspots for emissions. So because of this diverse production system, manure management practices, and the variation in climate, permit me point out that we also have the African swine fever, which has impact on measurement and emissions. So it implies that it's tricky in this area to mitigate greenhouse gas emissions. Next, please. So for methane emission, which is the focus of my presentation, I would like us to look at the production systems first. It's important because the production systems have a great impact on the emissions. So for productions, we're looking at poultry here, we're looking at swine, and we're looking at beef cattle. So for poultry, we have layers, we have broilers, and of course, free-range Brahma and birds. So for layers, it's predominantly kept indoors with the wood shaving as the bedding material. And the wood shaving is usually put at the beginning of the production period, and it's not taken out completely. So intermittently, it is removed. And based on need, there may be addition of wood shavings, but usually it's just a constant removal over the production cycle. And usually the manure is either sold to farmers or it is kept in a separate building where it's mixed with dewatered pig manure and then sold to farmers. Thank you. Next. Now for broilers, we have two predominant systems here. There's the wood shavings, which is applied on a solid floor, and there is the slatted floor system. So for the system with the wood shavings, it is applied usually at the beginning of the fattening period, and based on need, it can be applied intermittently again, but usually it is removed at the end of the fattening period. But again, if there's need, it could be removed within the fattening period. The fattening period usually lasts for about 2 months, 6 weeks to 8 weeks. And the manure is usually dried for crop production or sometimes used directly for crop production. Now for the slatted floor system, the fowls are kept on a raised cage. Since the droppings have to get into the slits underneath, and it's composted. You have also anaerobic digestion as one of the manure treatment options here. Let's get to the next slide, please. Now, if we look at broilers, the production systems, it's layers rather, no broilers. Broilers, we have those that are kept indoors, and we're looking at broilers which are kept outdoor. This outdoor production is not really popular it's actually popular, but for organic farms, it's not it's still coming into play. And it's not uncommon to see broiler production for this particular breed of birds that are kept outdoor. So usually we have the traditional birds kept outdoors, since they can resist the large variations we have in temperature, in rainfall, humidity, and they can manage the outdoor system. So increasingly, the organic farming is becoming a little bit popular, and the normal broilers, which are kept indoors, are being kept outdoors now. And the production of Brahma birds also, it's becoming popular, and they are reared outdoor in large quantities. So with this system, there's no bedding there. So we expect that the droppings, it gets into the soil and mixed with it. And in those sleeping areas, once in a while, it's cleaned and used for crop production. Otherwise, the birds, they have places where they can perch on, so they can just drop the droppings on the soil surface. Next, please. Now, when we talk of emissions, let's look at the methane emissions, for example. I put up a few studies, two studies here, which we carried out.
Martin, we have a little bit of problem listening to you.
Yes.
That was better.
Are you getting me now?
We are getting you now.
Oh, sorry. Yes. So I was saying that for the methane emissions, when we look at, let me open up my computer also. Yes, for methane emissions, we have two studies here that we've carried out. Actually, it involves greenhouse gases as a whole, methane, CO2, and nitrous oxide. But focus on methane emissions. We've put some numbers here for layers on wood shavings for two studies, from 0.6 to about 0.76 milligrams per animal per hour for emissions. When we look at emissions for broilers, they are higher than that for layers. So for two studies that we've carried out, methane emissions, we have them in the range of 0.9 to about 1.2 milligrams per livestock per animal per year. And interestingly, for the merge system where the droppings goes onto the soil surface, and the outdoor system in those sleeping areas, overnight sleeping areas, we didn't see any significant methane emissions there. That's why we have the kind of numbers that we have here as quite small. And from our studies, we've noticed that the emissions are influenced by the age of the birds, the frequency of manure removal. We have water spillage on the wood shavings. We have bedding material used and the age of the bedding material. And certainly the ventilation rate also affects the emissions of ammonia from manure management and broiler systems. That's layers, broilers, and Brahma birds. Now, with regards to cattle, we have predominantly the same kind of system that runs across Africa, from West to East Africa. It's free-ranged, and they have the sleeping areas where they spend the night, and sometimes resting areas. These are hot spots, and we've measured greenhouse gas emissions from this spot using the flux chamber method. Next, please. Now, for this particular study, we measured from two bands, two sleeping areas, and we have the numbers that we present here for methane emissions with a large range, a mean of about 573 kilograms per year. And let me just emphasize the basis on which this calculation here is done. Under the table, we have the number of animals in each sleeping or resting area and the surface area. And that's why we can give the emission per year and per head as well, as presented in the table. Next, please. An important part of emission from cattle is also slaughterhouses. These are really hot spots, since the manure is dumped on the same spot for a long period of time. Once we measured using the flux chamber method, and the interesting thing here is that on the same spot we have manure of different ages, and there is less turning and mixing. So methane emissions could be a bit high with a little of with maybe some small nitrous oxide emission, since we don't have turning. But it's important to note that the kind of waste we have here, it's a mixture: stomach waste, intestinal waste, blood, wastewater, all mixed. So this is a category of waste on its own, which is important to characterize and to know the kind of emissions that we have from it. Next. Yeah, from this study, we had emissions based on two methods. One, again, is direct measurement using the flux chamber method, which we present in the table. And the other one is we try to model. In fact, we model it using the IPCC Tier 2 approach, where we measure the VS. The VS is quantified from the waste collected in the dumpster in the slaughterhouse. And the B0 and the EMS, the methane conversion factors, we use standard numbers for the region from IPCC. Once more, I would like to note the importance to determine these parameters locally, since it will improve our estimate of methane emissions. That's the biomethane potential and the methane conversion factor. There's some work which we did on methane conversion factor together with Andrew van der Zak of AFC Canada, using the different agroecological zones we have in Canada. So it's important that in Africa we do the same kind of work so that we can have methane potentials and methane conversion factors for the different agroecological zones that we have in Africa. Next. The last category of animal that I've looked at here is pig production. We have predominantly on concreted floors, but also on slated floors. The slated floors are mostly raised so that we can have the waste underneath, which is collected and stored or used for crop production. We also have deep litter, which is not really popular as such. But the interesting thing with pig is that there's a lot of wastewater that comes from its production. So sometimes we have these channels where the wastewater is channeled into concrete tanks. And the concrete tanks, they're just like hot spots. Anaerobic digestion takes place in there, and a lot of methane is emitted from this hot spots. So it's good that we understand this different management system, so we can see the next slide shows us the numbers that we have for measurements there. Yeah, so in the next slide, we have numbers using, again, two different methods. We have direct measurements using the flux chamber method as presented in the table, but we also have model emissions, which we use, again, the VS, the B0, and the methane conversion factor to estimate the methane emissions. And I put here just a table to show how the VS increases over time, over weight, body mass, from about 20 to about 8 kilograms. And the methane emission also increases, since it is modeled based on the VS accumulation. The next slide. So in the next slide, we have some direct measurements from direct methane emissions from pig manure management. And here I would like to highlight two important aspects in this table here. The pig slurry, that's the wastewater, the tank where the wastewater is stored. That's when the barns are cleaned, the water flows into a tank and is just kept in there where sediments and the top part flows into streams. We measured from those tanks, slurry storage tanks, and we have methane emissions of about 8 milligrams per surface area per minute. But we equally measured from where the solid manure underneath the floors it's collected and together with content. So what sometimes the farmers do is that they get the peak manure, which has a high moisture content. They mix it together with the poultry manure, which has a low moisture content, to come to some kind of a middle number where they can easily transport it. And those who need it in the farms can easily buy and apply in the farms. So when we measured in a situation where the pig manure and the layer manure are combined, as well as the pig manure and broiler manure are mixed together, we have the emissions are presented in the table in this graph, in this slide here. Let's get to the next present. Now, permit me to point out here that with respect to manure management and the implications on greenhouse gas emissions, we are carrying out 2 experiments, and the preliminary results are presented here. In the first one, we are trying to co-digest livestock manure with palm oil waste. In West Africa, palm oil production is such a big industry, and the palm oil effluents, the wastewater there, it's rich in fats. So we are thinking of how to add the fat content in manure for anaerobic digestion. I think the wastewater from palm oil production is a big problem. We try to mix it together with livestock manure and do cold digestion to see how it mitigates greenhouse gas emission and produce renewable energy. And in the other experiment, we are also looking at types of composting and composting with amendments as well, to see its implications on methane emissions. And while the results are promising for window composting, we will note that just as it's standard, it has an implication on nitrous oxide emissions because of the tanning. So there's nitrification and denitrification. So these are areas where we need to work more on. The next slide. This is our last slide, and the important things we need to note here, which are the challenges, areas for future for collaboration and research. So there's need to determine local input parameters for greenhouse gas modeling. B0, biochemical methane potential, and the methane conversion factor. So it's good that we have these numbers for different management systems in Africa and different agroecological zones as well. The second important thing is that there's need also for year-long measurements to be able to appreciate seasonal variations. In that case, we may have better mitigation options. I also would like to note the difficulties it is to capture emissions from grazing. I mean, the grazing area is so large, it's difficult to actually measure what's happening in there and mitigate it. And there's need for more measurements to simultaneously mitigate methane and nitrous oxide emissions. Currently, we have a small research base in this domain, and with the collaboration, we were able to increase our research base. And there is need for high resolution measurements in terms of instrumentation and the frequency of measurement. And the last point, which is also an important aspect of this webinar, is the need for collaboration and networking. So with this, I would like to thank you for your keen attention. I understand that the internet signal has not been that good, and so you might not have received me clearly, but it's good that we have the slides there. Thank you.
Thank you very much, Martin. It was very interesting, and I must say I learned a lot from your studies, in addition to what I've learned before from Kenya. So, and I can see there are questions in the chat. So I think before I start to ask questions, we would like to ask the chat. Look in the chat. Yeah, well, yes, there was a question by Sega. I don't know if you have. Yeah, maybe I'll ask one of my questions. You're saying you're looking at these different management of chickens or layers, and so you're having them walking around outside in the organic farming and some in animal houses where you can manage the manure. So I didn't have time enough to compare your data. Well, from where do you think the emissions are largest?
The emissions are largest for indoor systems. For indoor systems, the manure is kept on, there's a lot of manure on one spot, but with the outdoor, you have the overnight sleeping areas, but during the day, they spread the manure on the soil surface in different areas.
Yes. And will it give a larger emission than if you have them indoor constantly, or? I understood that some of the chickens were only indoor and some of them were also outdoor.
Yes. No, the emissions are larger for those that are kept indoor.
Okay. Yes. And I have to look at. And then you are saying you also mentioned that it would be great to have more collaboration. No, I have another question first. When I saw your measurements and when you compared them to IPCC, my impression was that your emissions estimates were lower than from the IPCC. That's one question.
Yes,
is that correct? We can't hear you.
In some cases, they are lower because it's integrated number for different. It's important that we do local measurements in different countries so that we can have, a good spatial resolution of these numbers.
And then unless there's, I can ask one, because you were showing this biogas production, anaerobic digestion, and that was the palm oil I understood you were treating in a biogas plant. So what do you think, especially with this pig manure that is liquid manure, would it be feasible to produce energy and at the same time reduce greenhouse gas emissions, methane emissions from the stored manure? Is that an option in your country or in your systems?
You're talking of the case where the manure is mixed with a palm oil slurry?
No, yeah, and also in general, some of your pig manure is a liquid manure.
It's liquid manure.
Yeah. And you have methane emissions from that liquid manure, and then you could have anaerobic digestion. That we know it reduces methane emission.
Oh, absolutely. So in Cameroon now, the anaerobic digestion is becoming quite popular, and they are local systems. They are individual systems that people use in the small farms. So those portable systems. So yes, it's quite an option, which is its popularity is actually increasing exponentially.
And I'm asking, it's because it's interesting. So when you have this liquid manure and with your farmers, are they able to manage the liquid manure and spread it in the fields in the right amount so that it benefits the crop productions most possibly?
Now, this consists of liquid manure. So
yes,
for the liquid
manure.
System, yes, they carry when the manure is underneath the floor, they carry it out, then they wash it down, water in it. But the solid part, not the solid part, the initial manure, it's carried out and mixed with poultry manure from bedding, so it changes the moisture content.
No,
but in other cases, what they do is that yes, they take the solid manure and they dry it.
But I think maybe the liquid manure is more problematic.
Yes, I'm getting you. Yeah, Sven, did I lose you?
Oh, can nobody hear me or?
We can hear you, Sven. I think there's just a bit of a time lag between you and Martin.
Yeah.
Okay. Yeah, I can't get Sven actually.
If I
Yeah,
may quickly come in. So
yes.
Martin, basically what we had been discussing when Sven was here in Nairobi is that there's a push towards more biogas digesters because they have a lot of benefits. But the problem is that you then move from solid manure management to liquid manure management. And the question is, in your experience, how well can farmers handle the liquid manure? Did they find that challenging, or have they found good local solutions?
No, they find it challenging because they have to use a lot of water to start with. That's how they will generate liquid manure, the input water. And for cases where they can minimize water as much as possible, they will minimize it so they can cut down the volume of manure generated. So given the temperatures that we have in West Africa, it's easier to dry the manure, or when it's just exposed, the moisture content is going to drop over time faster. But as I say again, biogas is becoming quite popular, and for cases where they have dry manure, they still will add water to it to be able to anaerobically digest it.
Okay.
And then maybe as a follow-up, okay, then they have biogas digesters because they do slurry management anyway. So it seems that biogas digesters is a logical next step. But the question is, how do they handle the digestate, the bioslurry that is being produced after the digestion process? Because what I've seen here in Kenya sometimes is that people have a biogas digester and they use the biogas, but they don't really have the capacity to use the bioslurry, and they just let it drain into the soil, or they just use it on a nearby crop field, but not on crop fields far away, and it creates nutrient imbalances. Was that something you observed as well?
Absolutely correct. The means to transport the slurry, the digested for long distances, it's not there. That's the first thing. Then the second thing is that they usually apply just to the farms that are around, the crop farms that are around the digesters. That's the other thing. Then in most cases, the digesters are not very large digesters. Farmers are not big farmers to 1,000 pigs, for example. So they are small farmers, and the quantity of digested produced is not so much that it becomes a big problem to handle. So it's almost the same as handling the initial raw manure that is not digested. So they have the same kind of problems and they managing it for pig slurry.
Thank you.
So I wish to say thank you to you, Martin, and also to David and to Sonia for your presentations. And I think you have opened up for the work to be done in the future. And we just have a last comment, I think, that is in the question and answer chat. It's saying, interesting presentation of NACWA. Any chances of exploring collaboration with the University of Zambia? So I would say to all of you that it's not only, it's everybody. There's a really great to collaborate with all of us, between all of us. There'll be a conference there's a conference now in October in the GGAA. It's about greenhouse gas emissions and animal production in Nairobi. And I know that David, he will present, well, Sonia, you'll give a large presentation, which is not so much focused on this manure management networking, but David will give show a poster about our work in the manure management network. And I think everybody of you can go and talk with Sonia and David there. And we will, in the manure management network, follow up on this and see if we can provide some means. Well, we can always develop a network, but there must be something more than just having a network to meet. But there must also be some funding for doing a little bit of work together, or you can with Sonia and David talk about what you would like to do actually in the future together. I think that is Sonia and David. Isn't that more or less what we have talked about earlier before this? And of course also you, Martin. Sorry. So that is that is all I have to say. And I would like to say to everybody, thank you very much for being here and taking part in this meeting on Teams or conference. It's been great to be listening to the three very, very good presentations. So, and with these words, I say goodbye to all of you.
Goodbye. Thank you.
Goodbye. Thanks a lot for listening.
Bye, everyone.
Thanks a lot. Bye, everyone.
Bye-bye. It was good.
So, goodbye.
Goodbye.